So last class we developed the techniques for vector physics, dealing with motion in two dimensions. Today we're going to apply that to a problem, the problem of two-dimensional relative motion. So classical relativity, we're dealing with the relative motion of slowly moving objects. As you may know, as you get close to light speed, classical relativity does not work and we need special relativity. So we're looking at fairly slow-moving objects like trains, planes, and automobiles, moving through the air or on the water. Now, if you're moving on the water and the water's moving, well, interesting things happen. For instance, if you get in a boat and point directly across the river, you don't actually move straight across the river. No, you don't move straight across the river. Because if this is your boat motion, the river motion is actually going to push you downstream. And you'll end up with a resultant motion in this direction here. Now, oh, that's horrible. Motion, that's supposed to say. It's a vector sum. It's the motion of the boat plus the motion of the water. That gives you the resulting motion. So this is the way the boat vector is pointing, but the water vector is pointing this way. So you end up with the result that the boat moves in this direction. Now, as it's moving, let me just pull this over a little bit. Just want to add this. The boat still points in this direction, right? The nose of the boat is still going like that, still going across stream. But the water moves it sideways. There we go. And so that's the resulting motion along that track right there. Okay, so that's our idea in this problem, that if you've got a boat or a plane, then you've got to take the ship vector, the boat vector, and add the water or air vector to get the resulting motion observed relative to the ground. Let's look at a couple of examples. So let's imagine that your boat needs to move across the river. Let's say like there's a waterfall or some big rocks there. Now we saw that if you head straight across the river, if you point your boat this way, then you're going to get swept downstream. So if you wish to avoid getting downstream, being swept downstream, then your boat actually needs to point a little bit upstream. And if you get the correct upstream angle, then your resulting motion, which will be the sum of the boat vector and the water vector. Oh, these things are hard to select sometimes. So there's the water vector. That's the current flowing downstream. So the boat motion plus the water motion will actually give you a result that's straight across. This is called ferrying in canoeing or kayaking. And you've just got to point upstream at the correct angle. Okay, so here's the boat sort of pointed like this, right? Partly upstream. Here's the water vector. And now your result will be straight across. So in this case, the result was straight across. In the previous diagram, the heading was straight across and the result was downstream. So you need to pay attention to semantics a little bit to know which of those two diagrams you're dealing with. Is the heading or the boat vector straight across, as in the first drawing, or is the heading upstream and the result is straight across? So here, let's try an example. I'll give you a sec to read it, and then you should try drawing the diagram. See what you think it's going to look like. Here, your boat's starting here. Here are the banks of the river, and there's the current. So try drawing the diagram. Then we'll check together. Okay, so hopefully you saw in reading that if the boat wants to move straight across the river, that probably means we want a resultant that's straight across. So there's like a waterfall here and we can't get swept downstream. In order to do that, we have to point upstream into the current a little bit with our boat. So that's the way we'll point our boat. That's the boat vector. Then the current flowing downstream will give us a resultant motion that is then straight across. So that's what the diagram looks like. Now we can just do another triangle over here with the numbers on it to solve. We know this will be 90 degrees. Okay, so that distance doesn't matter here. So the current is 4 meters per second. And the boat's engine speed, how fast it can move in still water, is 6 meters per second. So there's a couple of things we could find. We could figure out what the resulting speed is across the river, but we're asked for the angle. So the heading angle. So we can see that the opposite side is 4, excuse me, and the hypotenuse is 6. That suggests the sine ratio. So sine, SOHCAHTOA, sine is opposite over hypotenuse, 4 over 6. So theta will be the arc sine or inverse sine of 4/6. Let's see what that is. 4 over 6, 2/3, of course. Inverse sine, 41.8 degrees. So we've got to aim 41.8 degrees. Oh, that's bad spelling. Upstream. That will be our heading to have a resultant that's straight across the river. Okay, now these first 3 drawings that we made are all nice because they were 90-degree triangles. That's not always the case. So one example where it isn't true would be, say, like an airplane navigation problem. So here we have a plane flying west at 300 kilometers per hour, but there's a wind blowing northeast at 100, and we're asked to find the resultant motion. So let's first draw that diagram. Okay, so we have a plane. Here's our plane vector going at 300 kilometers per hour to the west. Then there's a wind vector that we're going to add to that. So we'll add the wind motion to the plane motion to get the resultant motion. So it'll look like that. So plane plus wind will equal result. So this will be the resulting motion of the plane right here. And we just want to find out how much that is. We know the plane speed and direction, and we know the wind speed and direction. Oh boy, that's terrible. That's supposed to say result. Let's write that again. Right there. Okay, so that means we have to add 2 vectors. Now we practiced that last class, so we know that one way to do that is to find the components. So for the plane vector, it's pretty easy because there's no up and down component, and this is to the left 300 kilometers per hour, and we'll just stick with kph units. Now for the wind vector, it's northeast, which means 45 degrees. So it's 100 at 45 degrees, and so we want to find its x component, and we want to find its y component. Now the x component will be the adjacent side, so that'll be cosine. So you cross multiply the 100, this will be 100 cosine 45 degrees, and you work that out and it's 70.7. Now with the wind northeast, the x component's actually to the right, so it's positive. The y component is up, so it's also positive. And if you do 100 sine of 45 degrees to find the opposite side, you find that's also 70.7. So what we've just done there, come on you, there we go, is we've just, oh my goodness, this does not want to come with me. There we go. We've just found out how much this component is. It's 70.7. And we found out how much this component is. It's also 70.7. So now we would like to know what the components of the resultant are. Well, its y component's pretty easy because the plane had no y component. The y component of the resultant is just 70.7. How about the x component? Well, the plane vector was 300 in the negative direction. Oh, this is really a struggle for me. And the wind was 70.7 positive, so it's negative 300 plus 70.7 to find the resultant component there. So 300 negative plus 70.7, 229.3, if you just add those 2 numbers. Okay, and so that gives us the 2 components of the resultant. Oh, sorry. 229 to the left. So now our resultant, we could do it up on this diagram. This is negative 229 and this is plus 70.7. So this is our resultant, and we just want to know what its magnitude and its direction is. So for its magnitude, we're going to use Pythagoras. So we're going to square this, then we're going to add 70.7 squared. Oh, that didn't work. Okay, let me just pause and work this out. Okay, sorry about that. So here we see it's 239.9. So that's how fast you're going speed-wise as a resultant. And then for the angle, we use the tangent ratio. So tan theta is 70.7 over 229. So we do the inverse tangent, and that works out to about 17 degrees. Now this angle opens towards the north, starting from the west. All right, so we see that adding the plane vector and the wind vector to get the resulting vector, this is a relative motion problem, but it's also an application of our vector skills that we worked on last class. Now this is just a triangle, and as we mentioned before, you could use triangle trig, say the sine and cosine law, to find the resultant in the angle, and obviously you'll get the same answer. So in class, we'll practice some of these problems together, and then we will get a start on our study of projectile motion, which is another problem that we'll solve using vector algebra.